Right, so intrinsic viscosity of macromolecular solutions. So we've come to a point where we're going to deal with our first technique. Techniques are almost as important as the macromolecules themselves in biomolecular technologies. And if you're after a Nobel Prize, Nobel Prizes in chemistry and biology are as often given for the development of methods for studying large molecules as in their application themselves. Is that sufficient reason for considering methods? Maybe not. So after Nobel Prizes, then, but the ones for viscosity have already been done, I'm afraid. People like this guy, Einstein. Although he did his PhD on viscosity, but he didn't get his Nobel Prize on viscosity, I don't think. He drifted onto something else. What was that? Yeah, the less important thing of relativity. So viscosity, and it's a very simple, almost beautiful type of measurement in these wonderfully made glass tubes. Now this is a scientific instrument. Okay, this has been constructed beautifully by a glass blower. This is an expert who can make all these shapes and things with glass. And this almost like you want to almost like display it in your living room. It's so beautiful, and it basically contains a YouTube for obvious reasons. Has a small capillary. You can't see, but it runs along here. You can see it if you look at the notes on the Moodle. And in this capillary viscometer, you're just measuring how long it takes for liquid, this orange liquid. So it might be cytochrome or dilute hemoglobin solution. Goes from one mark to another. So you get the time, how long it takes to get from there to there. And it doesn't shoot down straight away because you have a very narrow capillary which controls the flow of liquid. But it's this flow property and the effect of dissolved molecules in a solution which represents the viscosity of solutions and can give us quite a lot of interesting information about the molecules, not just viscosity, but about the molecules themselves, as we will see. And yeah, I said Einstein did his PhD on this sort of work, and this is a paper published in 1906, which formed part of his PhD thesis. I had his PhD thesis translated into English. The original was in German, and it's only about that thick. It's just a couple of scientific papers, 2 or 3 scientific papers together. But it's gone. I don't know who's borrowed it or lent it to a student. Maybe last year's ABT Navies again. Yeah, must be them, mustn't it? So if I find it, I'll bring it and I'll show it to you. But any German speakers here?
But I know a bit German. I'm a Neubestimmung. I think it means a new introducing the modern molecule.
Yeah, Bestimmung is a measurement.
Yeah,
so
measurement.
Eine neue Bestimmung der molecular dimension, because you can always work out what the words mean. So a new measurement for molecular dimensions from of Einstein, die älteste Bestimmungen, the old measurements on the size, the growth of molecules, is embedded in the kinetic theory of gases. And Flüssigkeiten means the flow. Observing, beobachten, means to observe the flow. So it introduces this paper, which is about the measurement of molecule microdimensions based on flow properties, Flüssigkeiten, viscosity. And he published a formula which related the size of a molecule to the viscosity, or a viscosity parameter known as the intrinsic viscosity. What's going on here? And it was basically a shape factor, and for a sphere, this viscosity shape factor he worked out to be 1. And for some years people used this calculation, and then they found problems with it. You could work out things like Avogadro's number from this viscosity shape factor for spheres of 1, and people were coming out with quite large discrepancies, large errors. And then it was actually an assistant which looked at the paper, the original derivation of Einstein, and found that he'd missed out a whole series of terms in the calculations, and he got the wrong value. What should have been, what was 1 should have been 2.5. Right, that's an error of 250%, and that was by Einstein. Okay, well, we all make mistakes. So Einstein, the greatest brain there's ever been, can make this error, and that was in Annalen der Physik in 1906. So 5 years later, with his tail between his legs, you say in English, Einstein published a correction, Berichtigung zu meiner Arbeit, eine neue Bestimmung der molekular Dimensionen. So a correction or comments,
My work.
yeah, of my work, meine Arbeit. Vor einigen Wochen taten wir. So for some weeks, Herr Basselin, who was an assistant and also worked with Mr. Perrin, who also got a Nobel Prize actually for doing work on frictional coefficients of molecules. But Basselin this assistant had looked at his calculations and found out that he'd made these mistakes. Resultat erheblich falsch. That's wrong. Diesen Fehler, these errors will ich im Folgenden berichtigen. So these errors will I in the following correct. So it's a correction to his original paper. So it took 5 years to sort out, and the correct derivation gave this value of 2.5, which has been used ever since. So that's interesting, isn't it? That Einstein had worked on this, and we find that Newton also had a say in some of the early theory of viscosity. So all these famous scientists had their grounding in viscosity of solutions. Maybe it was these sort of beautiful viscometers which attracted them. It attracted me. Wow, that's great. Must do experiment. Yes. And in fact, you must do experiment, because we've got a viscosity practical designs just for you. So you can recreate the Einstein situation, not only making his errors, but those measurements that Einstein and Newton and Francis Crick did 2 PhDs. One, I think, was at the Royal Institution, where it was on viscosity of molecules. The second PhD was at the Cavendish in Cambridge on hemoglobin. That's why he was so old when he got his 30. They commented that on the film about him being 35 without finishing this second PhD. He also said that making viscosity measurements were one of the most boring things he'd ever done. So we will ignore that comment. Viscosity of biomolecules. So why do we measure viscosities of biomolecules? So viscosity is a measure of the resistance to flow. If you've got a liquid, how slow it flows means it's more viscous. It's also temperature dependent. So anyone who has a car or run a car, you put oil in sometimes. When the gauge goes to red, you put oil in. When I was a student, not a student because I couldn't afford a car as an undergraduate, but when I was a PhD student, I was doing some part-time work, and I was able to afford an old car, an old banger, we said, in those days, some ancient thing. And it was one of these cars that actually used more oil than petrol, if you know what I mean. So I don't know whether you've got one of those cars. No, they'd never be allowed on the road these days, the sort of things we drove. But putting oil in, oil is a very viscous liquid, but then when it heats up in the engine, it becomes very runny and then becomes an efficient lubricant. So it's a measure of the resistance to flow. And actually, when you add molecules to a liquid, like water, you increase the viscosity, and depends on the concentration, of course, but also on the sizes and shapes and what's going on in solution. So why viscometry? Viscometry, it's simple, straightforward technique for assaying solution conformation of biomolecules in solution, and also the volumes and solvent association, the hydration property, which we mentioned yesterday. Remember that specific volume and the swollen specific volume, how much molecules swell? Viscosity is a technique for doing that. And in the practical, one of the things you'll do is measure the swelling in solution of a protein. Let me think, what protein can we think of to use? Any guesses? It's Ranzu, it's all right. We just literally been talking about Einstein, that's all, so we haven't done anything scientific yet. But it was interesting, wasn't it? That's how Einstein had made a mistake. But he didn't make a mistake in choosing the topic for his PhD, because it's a very sensible topic, viscosity, much more sensible than relativity. Yes. Even more sensible than relativity, not to downplay the good work he did there too. So you can measure from the changes in viscosity caused by putting molecules in. And what was that molecule we were thinking of? That protein molecule? Of albumin, that's right. Interesting and inexpensive. What more could you ask for? Usually it's inexpensive if you're running a practical. Right, solution conformation of biomolecules and the volumes, the swelling. We can get the molecular weight of biomolecules in a very simple way, based on an assumption, and how bendy, how flexible molecules are. This is important when we're dealing with things like DNA or polysaccharides, how bendy, flexible molecules are. And viscosity is a simple way of doing it. Okay, here's a schematic YouTube Oswald viscometer. Uberloader is another type, but it has a second reservoir coming off. What you have is this tube, and you have a reservoir here. this large bulb. So you put your liquid in, usually inject it in this way, a known volume, and then it occupies that and runs through here until it reaches the same level. Or the capillary action actually brings it through a bit. Oops. But then you pump. Used to blow through a tube at one stage, which would never be allowed now in health and safety. But now it's done by automatic pumping, which pumps the liquid through the capillary into this second bulb here and above this mark, and then automatically, well, not automatically necessarily, either manually you switch off the pumping device, or expensive instruments, they have photo detectors so they can sense when you get past this mark. But these automatic devices are not quite so satisfactory from a learning perspective. So when you do the practicals, you'll be using manual timing and also manual switching off the pumping, which we think is a much better learning exercise than just pressing buttons. Agreed? Yeah. Or you could look at it in a way saying we don't want to let you loose on the more expensive equipment, although we don't trust you. Okay, so you pump the liquid through. When it gets past this top mark, you stop pumping, and then you let the thing just relax back under gravity. And it takes typically a minute, 2 minutes for water to go from here to here, because the capillary slows the process time down. And you just simply time how long it takes to get from there to there, with a stopwatch or using photo sensors. That's the Ostwald viscometer. There's a second type of viscometer called a cone and plate viscometer, where you have a fixed cylinder here, and then you have a rotating cylinder on the outside driven by this band system, and you put your liquid in between. Okay, and basically when this moves, it creates a torsion on this torsion wire, and this torsion is related to the viscosity of the liquid. The more viscosity, the more torsion for a given drive speed. And this is used for more sort of concentrated solutions of molecules, what we call non-Newtonian, because we can change what's called the shear rate by changing the speed of the drive. This is called a cone and plate or couette type of viscometer. You have a rolling ball. Rolling balls have a rolling ball. Yes. So you have this capillary tube as a little steel ball. You can see it just there. You see it? So it starts off at the top, and then it's released, and you time how long it takes to get to the bottom. And it goes inside this holder here, and you can vary the angle. So you can vary the speed at which the ball is going down. So you've got a ball moving through the liquid as opposed to liquid moving through a tube with the U-tube, or liquid moving between a cone and plate with the couette. Yeah, rolling ball. And this one here is the same as a U-tube. Where are we? It's just got the capillary just bent round several times, because by having a very, very long capillary, you can increase the resolution of the measurements that you're making. This is called an extended capillary viscometer, and this belonged to Michael Crete, who was the guy who did those DNA measurements I showed you in the lab the other day. So don't drop this. And you will be using this in the lab practical, I can guarantee. Not that you're, yeah, it's complex. Right, now viscosity is very sensitive to temperature. So if we're making measurements, we have to make sure that the temperature control is very good. And normally this is at least to plus or minus 0.05 degrees centigrade, and preferably to 0.01 degrees centigrade. So we want to keep the temperature as constant as possible to avoid errors caused by temperature variation. So we use an accurate temperature bath with accurate temperature measurement. There's the water bath. That in fact is like the viscometer bath that you'll be using for the practical. But this one has automatic timing devices, and you can just make out the photodiode sensors there and there. So liquid relaxes down through here and then past this top sensor and then past this bottom sensor. So the timing is triggered here and stopped when it gets to here. So again, this is a red solution, so it must be hemoglobin or something like that. Yeah. And also there's a density meter nearby. That's interesting. And you'll see why in a second. Right, so a bit of theory. You don't have to reproduce this. This just shows you where the viscosity comes from. And to show you that Newton also was involved. Einstein, Newton, you can't get better than that, can you? So for normal Newtonian flow, basically what we have here, imagine this is a stationary surface. This could be the stationary plate in the Conan plate, or it could be the glass side of the tube. Right? So this is liquid in contact with the glass, and when you get further and further away, then liquid moves faster and faster. It's not inhibited by the wall. So you have this gradient of velocity. So this represents a velocity gradient. And the force in this case is gravity. In the case of the Conan plate, it's the force of the torsion, the drive, the shearing drive. So this gradient of velocity. And this is given by, the gradient's given by dv dy, the change in velocity with change in distance in this direction, okay? dv dy. So how long this velocity, how this velocity changes as a function of this distance here. And the force applied, well, we call it the stress, which is the force per unit cross-sectional area. So F over A is the, there we are, stress or shear stress. dV dy is called the shear rate. And for a Newtonian flow, the shear stress is directly proportional to the rate of shear. So if you increase the rate of shear by increasing the speed, or changing gravity by going to Mars or somewhere, then, or if it's a rolling ball, just changing the angle so things move faster. Then if it's Newtonian, the shear stress will be directly proportional to the shear rate. And the constant of proportionality is defined as the viscosity. All right, that's viscosity. Torr divided by dV dy for Newtonian, well, that is a constant, dV dy. The units are, well, the SI units, centimeter, gram, seconds, are called dynes per centimetre squared. So dyne second centimetre to the -2. And we don't say that, we just call that poise. Poise. And it's related to Pascal seconds, which is the SI unit of viscosity. But we don't use SI units, we use centimetres, grams, seconds. And the viscosity of water, 20 degrees centigrade, is 0.01 poise to, or 1 centipoise, centipoise to, yeah, a close approximation. That's the viscosity of water. These units are not important for us actually, as we'll see in a minute. You'll see we don't need these units, because we're dealing with the changes in viscosity when we add proteins or polysaccharides or glycoproteins or DNA into the liquid. What happens if you dissolve a molecule in a liquid? Then you disrupt the smooth flow of the liquid. So there's a disruption here of these what's called streamlines. And what happens is you put a molecule in there, it tumbles because of this shear effect. And that results in a dissipation of energy and an increase in viscosity of the solution. That's what Einstein's calculation was basically. It was a measure of the increase in energy caused by dissolving a spherical particle in the solution and then relating that to the dimensions of the particle. Now, this isn't easy for us because we're not bothered about viscosities and poises, Pascal seconds and all this sort of stuff. What we're interested in is the relative viscosity. And the relative viscosity is simply the ratio of the viscosity of the solution containing the macromolecule to that of the pure solvent in the absence of the macromolecule, e to 0. So the relative viscosity equals the viscosity of the solution, and we use the Greek. Christina isn't here, is she? So our Greek expert isn't here, but that's a Greek symbol, eta. Eta. Eta, ETA, which in no pen. Yeah, I had a new pen yesterday as well. Should we go and sneak one from next door? That's how whiteboard was. So Greek eta, not N. So in the alphabet it's alpha, beta, gamma, delta. No, epsilon. That's equivalent to E, isn't it? So eta is equivalent to our H in the alphabet. ETA, which also stands for, that's right, estimated time of arrival. Good. So eta relative, eta R, is just the viscosity of the solution divided by the viscosity of the solvent. Yeah, water or sodium chloride solution at a ionic strength of 0.1. Yeah, you know what that means now, don't you? Ionic strength. So it's the ratio of the viscosity of the solution to the viscosity of the solvent, and therefore it has no units. No units, no poise, none of this, no units. And for a U-tube viscometer, the relative viscosity is simply the ratio of the flow time of the solution make the measurement there to there for the solution, and then T0 there to there for the solvent. And there's usually a correction for the density of the solution and the solvent. So for accurate work, for proteins particularly, we need to correct for the density of the solution and density of a solvent. So you usually find there's a density meter that's near the, here we are, there's a density meter just there. And sure enough, in our viscosity lab, there's a density meter opposite. Where are we? Here we are. Density of the solution and density of the solvent. And if it's water or watery-like, what's the density of water? One gram per mil, or gram per centimetre cubed, yes, at 20 degrees centigrade. It can change with temperature. And that's the density of your solution. But for low concentration work, especially for polysaccharides, which are very viscous, you don't need to have high concentrations to make measurements, then the density correction becomes very small. So for very viscous solutions, you don't have to worry about density corrections because you work at low concentrations. But for protein work, generally, we need that correction. Right, so how can we relate this to molecular parameters? Because the relative viscosity, so will depend on the size and shape of the molecule, but it also depends on the concentration. Because the more concentration you have, the more viscous. So if you imagine a sugar solution, it's low viscosity, but then you put lots of sugar in there, so you get a syrup that has very high viscosity. So same molecules, just a much higher concentration. Yeah. So concentration is important. So if we are going to use viscosity to infer shape, we need to eliminate the concentration contribution. And the first step is to define what we call a reduced viscosity. So the reduced viscosity, eta RUD, what you do is you subtract 1 away from the relative viscosity and divide by the concentration. Yeah, just take 1 away from the relative viscosity, and your relative viscosity should be greater than 1. If it's not, then you're in trouble. It means you made a mistake. The viscosity of your solution should be greater than the viscosity of a solvent. If it's different, then there's a temperature mistake or something has gone wrong. So you don't have negative viscosities. So, or negative reduced viscosities. It's it's nr minus 1 divide eta r minus 1 divided by the concentration. So if C is in gram per mil, then units of reduced viscosity are just the reciprocal of that, mils per gram. That's okay. So that's how we deal with concentration. Almost. But then there's a horrible thing called non-ideality. Well, first of all, you know how to measure concentration now, so that's not a problem. We can measure concentration to get that using either a refractometer. Yeah. Now, unfortunately, non-ideality reveals its ugly head. But what did we say about non-ideality? How do we sort of reduce non-ideality in solutions? What do we do to make things become more ideal? Dilute, yes, right. So we dilute as far as we can. Obviously, we can't dilute, so you can't make a measurement, but dilute. So to eliminate non-ideality caused by exclusion volume, charge effects, backflows and things, by analogy with osmotic pressure, which we saw yesterday, we measured the reduced viscosity at a series of concentrations and then just extrapolate the result back to 0 concentration. Quite similar to what we did with osmotic pressure yesterday. Yeah, just make measurements of a series of concentrations and extrapolate back to 0 concentration. Whether it be a polysaccharide or a protein or whatever. And when we get to zero concentration, we can't measure at zero, but we can extrapolate back to zero. Then in the limit, the concentration goes to zero, which is here. Then the value obtained for the reduced viscosity is called the intrinsic viscosity. And we give it, it's got the symbol eta, but it's got these square brackets around it. That means the intrinsic viscosity. And its units are the same as reduced viscosity, just mils per gram. And we call it the intrinsic viscosity because it no longer depends on concentration and these other effects. It just depends on the intrinsic or the own properties of the molecule, its size and shape. So by making measurements of a series of concentrations, we can get the, extrapolating back to zero, we get the intrinsic viscosity, which we can then use to work out our sizes and shapes and do those Einstein calculations and things as we like. Scientists always like to do things better. So an improvement on this measurement at a series of concentrations extrapolating back to zero is they have this double extrapolation now. So the conventional extrapolation of the reduced viscosity and back to zero, this is known as the Huggins equation approach and is given by this equation here. It's a straight line equation. The reduced viscosity equals intrinsic viscosity plus this constant, which is Kh times intrinsic viscosity and times intrinsic viscosity again, if you expand the equation, times concentration. So if you plot reduced viscosity as concentration, you get the intrinsic viscosity from the intercept here, and the slope is Kh, Huggins constant, times intrinsic viscosity squared. We're not bothered about that, we're just bothered about this extrapolation. And then Kramer had this alternative representation where that's the natural log of the relative viscosity divided by concentration, and the equation is similar but not the same because you've got this negative here, and this now is the Kramer constant. So if you derive an equation, you can call the constant after yourself. Yeah. That's terrible, isn't it, really? Kramer and Huggins. Kramer. No, but when I first started lecturing 34 years ago, I used to say that Kramer was, you know, the Gibbs function is not related to the Gibbs brothers on the Bee Gees. Yeah, but you wouldn't know who those are. But 34 years ago, people did know that. And there used to be a group, we've all heard of the Beatles on Liverpool. Yeah, who's heard of the Beatles? Yes, absolutely. But there used to be a group called Billy J. Kramer and the Dakotas, who we used to like. Your mums and dads may remember them, yeah. And again, he used to say that this Kramer had nothing to do with the pop group in the 1960s in Liverpool. So don't get confused by that. Not that you would anyway. So Kramer actually was an Austrian. Huggins, was he UK or American? Don't know. But Kramer was certainly Austrian. Or was he Swiss? Anyway, all this work was worked out in the 1930s. And what this did, this second equation, it provided a check. So you can extrapolate using the Huggins formula and extrapolate using the Kramer formula as a check. So you just make sure you haven't made a mistake. And then this should, from the common intercept, oops, that gives the intrinsic viscosity. Now, some bright spark or pair of bright sparks saw that this line went up and this line went down. And then had the idea, why do we combine these two together? And you get a line that goes like that, which means that you could make your measurements of whatever this thing is at a particular concentration, and it's not that far off what the true intrinsic viscosity is. So it avoids the need for doing a concentration extrapolation. And the bright people who saw this were Solomon and Sayuta, who combined those two relations together. Oh, by the way, there is this little variance on the Huggins equation. That's just a minor variation. And came up with this Solomon-Sayuta equation. That means about, okay, approximately. That isn't a mark on the screen. That means about. So intrinsic viscosity is about 1 over C times this relation. So that means you can make an estimate of intrinsic viscosity at a given concentration. And that's important when you can't do a concentration extrapolation because you haven't got enough material. And also it's very useful for these new generation viscometers which you couple on the end of size exclusion columns. You haven't done that yet, but when we do the size exclusion chromatography lecture, you'll see put a viscometer on the end, and there you just measure one concentration. It's a special type of viscometer, which I'll mention later. Right, so intrinsic viscosity. We've measured intrinsic viscosity now. Yeah, what's difficult? We're just going to measure flow times and measure concentration accurately. And do an extrapolation, or a double extrapolation, that way, or use the Solomon-Sayuta equation if we haven't got much material or whatever. We can get our intrinsic viscosity. Okay, what do we do with it? Right, so when we found this, having made all that effort, we can make inferences on the shape, flexibility, and also the time averaged water binding, because don't forget it's a dynamic process. And also for non-spherical particles, we can estimate the molecular weight. Can't do it for spherical particles, you'll see why. And these are some of the values for intrinsic viscosity. Sorry, that 3.8 should be over here. I don't know what's happened there. Formatting error. Again, this should be over here, 700. That should be 200,000. Does it come out as errors on? Yeah, we'll do. You have the same as me. This shows you the variation in the intrinsic viscosity with molecular weight for different types of shapes, globular shapes and also rods and coils. So for globular particles, glucose 3.8, myoglobin 3.25, ovalbumin 3.49, hemoglobin 3.6, soybean 11S globulin, well, it's completely missing here, so not only is it a formatting problem, it's just not there, but that is around the same. It's about 3.5, 3.6. Our favourite virus, we have these favourite things, don't we? Proteins, polysaccharides. Our favourite virus is tomato bushy stunt virus, which is a big virus. Doesn't harm us, but it harms tomatoes. Yes, so it harms those guys there who work on tomatoes. They don't like TBSV. 10 million molecular weight. 3.4, no difference between glucose, in fact less than glucose. So for spherical particles, intrinsic viscosity isn't that sensitive to molecular weight. You can't use intrinsic viscosity to get molecular weight information. It just shows no change at all. But when you get to rods and coils, then things start to get more exciting. Fibrinogen, rod-shaped protein involved in wound healing. 27, Myosin, a larger rod-shaped protein, 217, and alginate, which is a coil type of molecule, so stiffy coil, has a value of 700. So you can see that when you depart from spheres, then the viscosity rockets up. So it's more sensitive to shape than molecular weight, really, as a parameter. Right, so how do we get shape information from 2012? Gosh. This wonderful parameter called intrinsic viscosity. It's a shame you can't. When we had these on overhead transparencies, you could just put a piece of paper and then slowly introduce it line by line. You can do it on PowerPoint, but it's messy. Right, so the intrinsic viscosity equals this symbol here, which is the Greek symbol nu. That's nu. Nu. Okay, and so Christina would confirm that. So that's Greek symbol nu times Vs. And Vs we saw yesterday was the swollen specific volume of a macromolecule, which for proteins we said was about 1. Yeah. So intrinsic viscosity equals the shape factor times Vs. And this shape factor is known as the Simha-Saito function of shape and flexibility. So Simha made the original derivation in 1940, and Saito in Japan made a similar derivation around the same time, maybe a few years later. Japan, Saito, yes. So, well done, Japan, on that. And what happened was Saito, he did this calculation in a different way to Simha, and couldn't understand how Simha got the right result, because he took the wrong approach. And Simha got the. Later on, we looked at this when I did my PhD. So everyone doing PhDs on viscosity, even me. We looked at the old Simha-Saito equations and derivations, and we found that Simha had also missed out a whole series of terms in his calculation, but then he made an error in the calculation as well, so the two compensated, so he ended up getting the correct answer by making two mistakes. So Saito was correct in saying he doesn't understand how Simha got the right answer, and we were able to show that we've identified the two parts of his calculation that he went wrong. He was just very, very lucky. The two compensated, and Simha got all these prizes from the American Chemical Society and all this sort of stuff. And poor old Saito really should have got the prize, prizes, not Simha. Anyway, that's gone. And actually, I had some correspondence with Saito when I was doing my PhD all those years ago. Saito was still alive at the time. Right, so that's the Simha-Saito function of shape, and it takes a value of 2.5, which is the Einstein value for spheres. The correct Einstein value, what he originally gave it as 1, and it's greater than 2.5 for other shapes. So 2.5 is the minimum value for spheres. Vs is the hydrated or swollen volume of the macromolecule per unit mass, and this is the equation I gave yesterday. V bar, which refers to the, what's V bar? Yesterday we said it referred to the dry molecule, the anhydrous molecule. And delta is the hydration, and rho is the density of the water. In the practical, you'll get used to using these, so you'll get some practice with this. And we also define something called the swelling ratio, SW, which is the ratio of Vs to V bar. So it has no units. It's the ratio of the hydrated specific volume to the partial specific volume. So it's a measure of how swollen the molecule is. And it's very useful talking about polysaccharides actually, because polysaccharides do swell enormously. Here we go. So the three forms of equation 1 here, just changing what Vs is here, is that one, or in terms of the swelling. And for proteins, again, we gave these values yesterday, and the swelling ratio is about 1.4 for proteins, about 1.4 for globular proteins, and is much greater than that for polysaccharides because of the greater affinity to water. So that's the equation which relates the intrinsic viscosity to shape and to the volume of the particle. So if you measure the intrinsic viscosity and you assume that if it's protein, that it's globular, and you assume it's spherical, so that has a value of 2.5, and we know what the partial specific volume is. We can use a program called Perkins, that's right. Then we can work out how swollen the volume is. Conversely, if you know the hydration of the molecule and know what the V bar is, so we know what the hydration or swelling, we can work out what the shape parameter is and work out the shape of the molecule. You can't work out both from intrinsic viscosity. It's one or the other. If you want both, you have to have some extra information coming in as well. But it's useful if you've got something which is globular for working out the hydrations. If you know the hydration from some of the measurements, which you can work out actually, because the program Perkins will also estimate the hydration of the protein or glycoprotein molecule, then you can, if you know that, you can use the measurement of intrinsic viscosity to get the shape of the molecule out. And this is how the shape parameter nu varies with axial ratio. I'm going to mention these in the lectures. Yeah, ellipsoids, prolate, cigar shape, oblate, which are the Smarties, M&Ms, minstrels. Which are the chocolate ones, M&Ms or minstrels? Minstrels are more sort of disc shape. Yeah, minstrels. So I used to bring in packets of Smarties and distribute them. And then they'd stopped getting them, I think, in the shop. Last time I looked, which was 4 years ago, actually, they didn't have them. I've got out of the habit, so apologies for that. And this is how the intrinsic viscosity, the viscosity increment, shape factor, changes with axial ratio, the ratio of the long axis to the short axis. And prolate ellipsoids have one long axis and two short axes. Oblate or disc shapes have two long axes and one short axis. Okay, so oblate goes like that, and prolate goes like that. So you need to know beforehand whether you've got a prolate or oblate, which your protein best approximates. In fact, most proteins are more prolate. Exceptions are, for example, the FC fragments of antibodies, which are more disc-shaped molecules. And you can use this wonderful program called ELLIPS1. When I say wonderful program, it usually means no, I wrote it. Okay, that's why they're wonderful. And they're free as well. Yeah. So you can download it from our webpage. In fact, during the practical, you'll be using ELLIPSON. So what happens is that the first part of the practical is at room temperature, and we're assuming we make a lot of assumptions. We assume the evolving molecule is spherical, and from that you can work out the swelling, the hydration of the molecule. And then after that, what we do, we whack the heaters up. So that was at 20 degrees centigrade. Then we put the heaters on full blast, and then you follow the change in the viscosity, the relative viscosity. You've got to correct for the fact that the water, the solvent, is reducing, but there's tables to help you do that. So you follow the change in viscosity with temperature. And what happens when you heat proteins up? They denature. Okay, so you follow the denaturation. And when the protein is fully denatured, what we do, again, make a big assumption. You assume that the swelling of the protein molecule is the same as you found in the first part of the experiment. A big assumption. And then you, from the final value of the reduced viscosity, which you approximate as the intrinsic viscosity, or use the Solomon-Sayusa equation, and from that, using the value of the swelling that you found in the first part, you can work out what the new value of new is, and then either read off from the graph or use the computer program. Just type in the value of the of this here, and it'll tell you what the axial ratio is, and also draw you a shape for a prolate and an oblate ellipsoid, which you can then transport into your write-up. So, yeah, nice practical. Right, good. So that's simple globular shapes we can get from simple intrinsic viscosity measurements. You get an idea of the shape of a molecule. Can't get the 3D structures, of course, with this. This doesn't do that, but it does give you an idea of the shape of the molecule, and helped us, for example, show that egg albumin was egg-shaped. Exactly. For more complex models, we can use what's called bead models. And can anyone guess why these are called bead models? Beads, yeah. We did mention this in the other course, how we construct with beta-lactoglobulin. So the idea is that you use programs. Can you read that? You can't, because it's on 2 lines and it's off the end of the screen, unfortunately. But it's Biophysical Reviews, and it's 2013, and it's in the on the Moodle link, so you can get that paper. So with Jose Garcia de la Torre, Spanish speaking, yes, yeah. So Jose from Murcia. We used to have this exchange of students over many years. Our students would go across to Murcia, and Spanish students would come over here and always complain about how cold it was. I don't know quite why. There's a student called Beatrice, who was actually behind some of this programming. So SolPro is a computer program whereby you can work out the orientation by this multi-bead approach. You can work out the orientation of these domains, Fab, and FC domains in an antibody molecule. So by a particular shape, you can calculate what the viscosity is, other parameters like the gyration radius I mentioned, and the sedimentation parameters. And then you do your model and then find out, calculate what the parameters are, compare them with the experimentally measured parameters, and then just change the model until you get agreement. That's called bead modeling, and that's what the program SolPro does. So you change, refine, or iterate the model until calculated and experimental values agree. And using this method, we were the first to show that the antibody IgE, which is involved in inflammatory responses, had a crimp or cusp shape in solution. Some 10 years before NMR scientists showed the same thing. So using viscosity, sedimentation, and other parameters, we could show that. Right, coming near the end. How much far have we got to go? Yeah, another 10 minutes. Okay, another 10 minutes? Yeah. Okay, for 10 minutes. Right, for general conformations, you see, this is when you, in your feedback, you put good coordination of modules. You've seen how well we got things like the volume, specific volumes came in. Nonlinearity came in because we've just done that, and that's fresh in our minds. We've done the Howe triangle before, yes, and this is how it comes in now. We have these extremes of conformation: sphere, rod, and coil, and the conformation of a given macromolecule is somewhere a locus along the sides of this triangle. Remember that? Proteins down here, polysaccharides along here, and DNA, denatured proteins along here somewhere. Well, viscosity allows us to locate where on this triangle our molecule is. And this comes from, for viscosity anyway, this relation called the Mark-Howing-Kuhn-Saccharada equation, right? Guess which one's the Japanese guy? Saccharada, that's right. So Mark-Howing-Kuhn-Saccharada. Mark was German, Howing is Dutch, Kuhn is Swiss, and Saccharada is Japanese. So how come all these guys are on this equation, which links intrinsic viscosity with molecular weight by this conformation or power law parameter A? So how come we got all these names? Well, it was in the 1930s when Mark in Germany, I think it was, came out with this equation describing intrinsic viscosity related to molecular weight, this power. But unknown to him, Howing in Holland had made the same derivation. So it became known as the Mark-Howing equation. And unknown to them, Kuhn in Austria had also come up with the same equation. So it came out as Mark-Howing-Kuhn equation. And then years later, it was discovered that poor old Saccharada, again in Japan, and he published his paper in 1938, 1939 or something. And it wasn't a good time to publish in those days because the whole world was tearing itself apart. So poor old Saccharada's derivation got forgotten about until some 10 years afterwards, when people were going through Japanese annals and things and discovered that he got the same equation. So groans, we got to add another name, and it became known as the Mark-Howing-Kuhn-Saccharada equation. So everyone's happy, we're correct, or just the MHKS equation for short. Right. That's a nice example of political correctness, and also several scientists coming to the same conclusion, working quite independently. And you've got similar relations to the in diffusion using a technique known as dynamic light scattering, which you'll meet in due course, and the radius of gyration, which we measure using X-ray scattering, and our friend Steve Perkins is an expert on that, or light scattering of solutions, and we'll meet that in due course, because light scattering is a very important technique in terms of biomolecular technologies. So by determining this, don't ask me why that's minus epsilon, and this, ABC, and minus epsilon. Yeah. So by determining these, we can pinpoint the conformation type of the molecule. Homologous series means they belong to the same series. They're all globular, or all rods, or this type of thing. Yeah. So you've got to use the appropriate relation. So, for example, this is our Haug triangle, and these are our extremes again. For some reason, this approximate sign has bounced up. It should be there. So we've seen how for globular proteins, what table I showed of glucose and our favourite virus, TBSV, hardly changing at all, the intrinsic viscosities. So when something doesn't change at all, the power law coefficient is 0. The intrinsic viscosity depends on m to the power a. M to the power naught is 1. So all you're left with is this constant in front, so it doesn't change with molecular weight. So A equals 0, sphere. For a random coil, flopsy type of molecule, like alginate or pectin or these types of polysaccharides, then it's between 0.5 and 0.8. And for a rigid rod type of molecule, like the polysaccharide schizophyllan, or schizophyllan, we say, in my part of the country, which is schizophyllan, chicken, encyclopedia. No clues? Chicken. Who says chicken on TV? Not seen John Bishop? No. Oh gosh. I gave you a clue before with the 1960s pop groups. No? Where did I say they were from? Schizophyllan. No, okay. It's the way people in the Liverpool area pronounce schizophyllan. All right. So that's I like schizophyllan. It's a nice term. That's what schizophyllan is a very rigid rod-shaped molecule because it has a triple helix, which gives chain rigidity to the molecule. So DNA is also quite stiff because it's double helix, whereas mRNA is a single chain molecule. It's quite flexible. It's a random coil type of molecule. So rods 1.8 and random coils 0.5.8. Okay, right. So the intrinsic viscosity is ideal for monitoring conformation change. It's very sensitive to conformation. We've seen that. So looking at denaturation of a protein, you can see how the intrinsic viscosity increases with temperature. And that's what you'll find in the practical, hopefully. But you'll find it doesn't do that when we look at evaldamin. Or if it does that, then that'll be quite remarkable. It doesn't do that normally. And your task is to explain why it doesn't do that. So from your vast knowledge of biomolecules and their technologies, which you'll have accumulated by the time you do the practical, you should be able to answer that question. But normally, proteins followed this behavior. Intrinsic viscosity, globular, denaturing, and plateau when everything is denatured. Okay, so but Waldman doesn't do that. When we look at it, not at the intrinsic, we don't use the intrinsic viscosity, we use the reduced viscosity for looking at the denaturation profile. And it's all related to what Waldman does when you heat it up. It doesn't just denature, it does something else. You think where it comes from. What happens when you boil an egg? Right, good. So intrinsic viscosity is also ideal for monitoring stability. So in biopharma, it's used as a very simple to use technique for looking at stability of drug types of macromolecules. So stability of glycovaccines, antibodies, this sort of stuff. It's used as a monitor for stability, particularly with polysaccharides. And this shows you a chitosan, which comes from crabs, and it's been used in nasal drug delivery. This is Monica Fee's PhD from 2006. And you can see how the reduced viscosity, we haven't bothered doing the concentration extrapolations. Reduced viscosity is a good approximation to the intrinsic viscosity for this type of measurement. And you can see at 4 degrees, the reduced viscosity stays reasonably constant, drops a little bit from 650 to 600 over a period of 8 weeks. So there's some degradation, but not much. At 25 degrees, room temperature, with warm room temperature, there is this degradation here, more dramatic than if we kept the material in the fridge. And say if we were on an airport in Saudi Arabia or something where it's 40 degrees, or in the south part of Spain, then this degradation is much more dramatic, but you can see how it bottoms out after it's degraded so far. It bottoms out. So intrinsic viscosity or reduced viscosity measurements are a very simple way of checking for stability of macromolecule based drugs. Yes, not so much spherical, unless you're looking for denaturation. It's not very good for looking at degradation, because the intrinsic viscosity for globular proteins doesn't change much with change in molecular weight degradation.
Sorry, Steve. Me and Jake had a meeting. Gary in about 3 minutes.
Okay. You can go. All I was going to show you was this, but maybe we can talk about this next time. This is, well, we'll mention this when we do the nucleic acids. This is the use of viscosity to show hydrogen bonds in DNA. Yeah, so we'll do that next time.
Yeah.
We've had enough anyway. We're both, all of us, tired. Here's some references. There's this wonderful review here, wonderful being, and this wonderful book. There's a new edition of this out now, actually, which when we do the polysaccharide module next year, we'll do this. But this is very good, and I've got this on the Moodle for you, the Seriduc, Sakai and Sakai. So it's more useful really when we go into more detail next semester. If you do, well, ABC's no choice, but if ABs do the structural biology module, then this will be useful for you. Right, good, done.
Do I have to remember the Harding equation and Caramel equation to do the calculation?
Yes, you need to remember those two equations. You need to remember. Okay.
Yeah.
This shouldn't be too difficult. But don't worry about Solomon's iota and all these things. You don't have to remember that. You need to remember the Mark-Howing equation. Okay, Huggins equation, not the Kramer, Huggins equation and the Mark-Howing equation. You know, this one here.
Here.
Yes, you need to remember this one. I need to remember what the values of A are for the different cases. The spheres, A is 0 for the rod, 8, and for coils, 2.8. Yeah. And this value for spheres, the correct Einstein value, that's right. Right, that's it. And things like this, V bar for a protein. You weren't here, you would know. Okay? Things like that. Need to remember. But we recorded the lecture anyway, so you can always play it back. And yesterday's lecture you missed. And also Emily missed the lecture today, so she can play this one back. Did I save? Am I still recording? Let's have a look. Yeah.
Stop.